All right. Thank you all for coming back. So our next speaker is Fraser Tweedale from Red Hat, and his talk is called Cooking with Cryptography. Please welcome him.
I just noticed that my clicker interferes with the sound. Anyway, yes, thank you for coming to my talk. I'm Fraser, and I'm an identity management engineer at Red Hat, where I work on free IPA and the dog tag public key infrastructure. So at work, I'm mainly using Python and Java, and I write a lot of Haskell at home. And I'm going to talk about cryptography, the library. So the outline of this talk, just a bit of background to the cryptography library, a quick overview of that library, and then we'll look at some real-world use cases where on the identity management team in free IPA and some related projects we're actually using this library, and then I'm just going to conclude with some resources. First of all, some words of warning. These are things you should never do, probably in order of most egregious to slightly less egregious. Don't ever invent your own cryptography algorithms or constructions. I'm probably pretty confident to say that there's no one in this room, including myself, who's smart enough to do that. And if you disagree with that statement, and are able to convince me that I'm wrong after the talk, then beers are on me. But don't write your own implementations of crypto primitives either. It's very difficult to get right and to write a secure implementation of a cryptography primitive. There are all kinds of side channel attacks. So these are attacks that attack not the mathematics of the cryptographic construction, but aspects of the implementation and what happens when that implementation is executed. It's very hard to get right. Leave it to the experts. Also, don't use low-level crypto primitives. Even if a library provides them for you and it's a secure implementation, you should avoid using low-level crypto functions as much as possible, because often they're difficult to use correctly, even when the implementations are secure. And finally, if you know that you do need to use a particular crypto primitive at a low level rather than a high level recipe implementation, then make sure that you're using it for the right purpose and that you're using it in the right way. For example, a cryptographic digest is not an appropriate way to hash passwords for storing on disk or in your database. They're also not secure as message authentication codes in general. Some are, many are not, including the SHA families, or SHA-1 and SHA-2 family. And with using crypto primitives as well, sometimes there are parameters and there are rules about what the values need to be. For example, a value in DSA or elliptic curve DSA, nominally called K, has to be different every time you call it. If you do two signatures with the same K value, then you can just easily compute the private key that was used to create the signatures, and that's how the PlayStation 3 was cracked. So a bit of a background now to crypto libraries in Python. There's a number, including M2Crypto, PyCrypto, and PyOpenSSL. They have various problems associated with them, or various shortcomings. None of them are inherently bad, but variously they are lagging in support for Python 3 or alternative implementations like PyPy. Some of them have insecure implementations of some primitives, or bad APIs that are difficult to use correctly or have poor defaults. So in other words, you can't just use the default form of a particular primitive or the function for using that primitive and expect it to be secure. So you need to know more about how to use the library correctly than what is at first glance presented in the documentation. They're also variously, again this doesn't apply to all of them, but some of them are missing some modern primitives and modern cipher modes, for example, like AES Galois counter mode. Don't worry if you don't know what that means, but it's a modern cipher mode for the block ciphers, including AES, that is desirable to have in a modern crypto implementation, and increasingly real-world users are moving to these more modern primitives because, as Bruce Schneier says, attacks on crypto never get worse, they only ever get better. So older constructions are often more vulnerable, if not completely broken. And finally, there's a lack of high-level APIs for common use cases. So often you don't want to care about the details. In fact, you shouldn't want to care about the details most of the time. You just want to say, sign this message or encrypt this message with a secure key. And so I know I can just transport it from this host to this host securely. You don't want to have to care about the details and burden yourself with the duty of getting it right if you're using low-level crypto primitives to do these jobs. There's also global interpreter lock or GIL issues with some of the libraries. For example, when calling out to the C implementation in pyOpenSSL, so it's a binding to the OpenSSL C library. It doesn't release the GIL, so if you're using Twisted, for example, while it goes and does a potentially computationally expensive operation in the OpenSSL library, your whole interpreter is locked and nothing else is going to run. So these are just a brief overview of some of the issues variously plaguing some of these crypto libraries. So enter the Cryptography library, which was started by Alex Gaynor in July 2013, and this was shortly thereafter followed by the formation of the Python Cryptographic Authority, or PyCA, which became the custodian of the Cryptography library, along with a number of other crypto libraries written in Python. It supports Python 2.6, or at least the current version supports Python 2.6, 2.7, and 3.3 onwards, and PyPy as well. So the goal of the Cryptography library is to become Python's cryptographic standard library. So when you know that you need to do something involving cryptography, signing a message, encrypting a message, even things like password hashing, it's your go-to library. That's where they want to get to. It aims to provide high-level APIs for common use cases, but to also provide most of the primitives that you'll ever need if those high-level APIs for the common use cases don't quite fit the bill. And yes, it's batteries included, so it includes most of the crypto primitives that you're ever likely to need. If you do need to, if the high-level APIs prove insufficient for your use case. This is in stark contrast to the philosophy of libraries like SALT, which is how you pronounce NaCl, which is by Bernstein, who, if you know anything about him, is a very opinionated but talented cryptographer. And so the philosophy of SALT is basically we provide one implementation, or occasionally two, for each kind of cryptographic operation you want to do. So there's one block cipher, one stream cipher, one message digest, one elliptic curve signing algorithm, and so on. Also, they strive to provide a stable API. What does that mean? Basically, they promise not to break the API unless they have to because there's a security issue. So that's about the only thing that will cause them to deliberately break their API. Installation is obvious, just pip install. Okay, so we'll take a look at the API of the library now and what is actually provided. So it's split into two layers. The first layer and the layer that will hopefully meet your needs most of the time is the recipes layer. So these are the high-level APIs that are safe to use and require developers to make very few decisions. relieving the developer of the burden of using the low-level primitives correctly. Currently, there's recipes for symmetric encryption and for X509. We'll look at these one at a time. So the symmetric encryption recipe is FINET, which is a construction that emerged from Heroku, I think, and is used in Keystone, OpenStack Keystone, and in a number of places in FreeIPA and the Red Hat identity management projects. So the specification is up on GitHub. The construction uses AES 128 in cipher block chaining mode for the encryption and uses HMAC SHA-256 for message authentication. So it's not only encryption, but it's authenticated encryption. Symmetric encryption, so the same key must exist at the point of encryption and decryption for this scheme to work. It also supports simple key rotation with this multi-FINET type, which basically you give it a list of symmetric keys, and when encrypting it will just use the first, but when decrypting it will attempt to decrypt a token with each key in turn until it either succeeds or runs out of keys. So it's a facility provided for you to rotate keys if you need to. This is what it looks like. So from cryptography.finet, import finet, and just an arbitrary message here that we'll use as an example. Generate the key, which is just a static method of the finet class, and spits out a 32-byte base64 URL encoded string. So the 32 bytes is what is base64 URL encoded, so it actually blows out to 43 or something. Those 32 bytes are two 16-byte portions, one of which is used for encryption, the other is for the MAC. MAC is a message authentication code. You then construct the FINET cipher engine by applying the FINET constructor to the key, and then to acquire a token, which is an object that contains some metadata and the encrypted message and the message authentication code. You just call f.encrypt, apply that to the message, and you get out the token. And the token is also base64 URL encoded. So provided it's not absurdly long, you can stick it in HTTP headers or these sorts of places. It's designed to be plugged in to most kinds of protocols and be transported safely. On the other side, for example, if this has been transported across a network, you need to construct the FINET with the same key, shared key cryptography here, and then you just try to decrypt the message with f.decrypt and the ciphertext, and that will either succeed and give you a message or throw an invalid token exception. For the X509 recipe, X509, if you don't know, is the prevailing public key infrastructure. So SSL or TLS uses X509 certificates. All of your browsers and operating systems have a store of trusted root certificates, and then those certificates a chain of those certificates can be validated to authenticate a network endpoint. For example, github.com or wherever you want. Your bank should be using TLS. If they're not, find another bank. So RFC 5280 defines the formats for certificates and for certificate revocation lists, and these are both supported in cryptography.x509, as are certificate request objects, or CSRs as they're often known. The standard here is PKCS10, and that's the RFC 2986, and it supports all of the common extensions that you see in certificates like subject alternative name, basic constraints, authority information access, and subject key and authority key identifier, and so on. So a simple example here, we're just going to generate a certificate request, and then we might transport that certificate request to a certificate authority for signing. So From cryptography, import X509. We construct a name attribute. This is the subject name for the certificate, foo.com. Yeah, we want to set up TLS for foo.com. And a subject alternative name for www.foo.com. We construct a certificate signing request builder, set the subject name, add the subject alt name extension with the alt name defined here, and then we can just do builder.sign with our private key, which is generated elsewhere. That's out of scope of this slide. We're going to sign it with the SHA-256 hash and use the default backend for this operation, and out we get a certificate signing request object. I'll talk more about backends in a couple of slides. So now we move away from the recipes layer, and again, I do hope to see more and more recipes kind of be implemented there. At the moment, it's just the symmetric encryption and authenticated symmetric encryption with FINET and X509. We come to the hazardous materials layer, appropriately called cryptography.hazmat. So yeah, consider that an admonition. So this provides all of the cryptographic primitives supported by the cryptography library, and the safety is off. It's up to you to use them correctly. The primitives supported by cryptography at this point in time for message digests, or hashes as they are often known, SHA-1, the SHA-2 family, which is SHA-256, 384, 512, and there's a bunch of other ones, including MD5, but most of them are esoteric or archaic, and you wouldn't normally be using them. HMAC, which is hash-based message authentication code, is the symmetric MAC provided by cryptography. One-time pads, so for doing your tokens on your phones and whatnot, HOTP, hash-based OTP, and time-based OTP implementations are provided. For key stretching, which is essentially secure ways to hash passwords, or actually, no, not necessarily. It's secure ways to take, for example, human input and turn that into a whole lot more entropy. So if you have a user typing a password in and you want to do a symmetric encryption of a key on disk or something, then you'd use a key stretching function to take what is a small amount of entropy from a user and turn it into a whole lot of entropy that's suitable for encrypting a key. So there's a password-based key derivation function 2 and HKDF, which I think is hash-based key derivation function. Block ciphers include AES and that's Advanced Encryption Standard and Triple DES. Public key algorithms provided by cryptography include DSA, RSA, elliptic curve DSA, and Diffie-Hellman, which is a key exchange protocol. And serialization formats are also provided by this library, and they include DER, which is an as-and-one serialization, PEM, which is kind of just a wrapper around DSR that adds a bit of metadata, and the OpenSSH key format as well. Okay, so backends provide implementations of the primitives for the cryptography library. There are a number of interfaces provided by the library that define they define the interface for implementing these primitives. So if you're going to write an implementation, they should conform to this interface, and then you can use the object that provides these attributes that are implementations of these interfaces as a backend for the cryptography library. So these include cipher backend, hash backend, and there's a bunch more. I'm actually not going to show these interfaces, but if you're interested, or if you're interested in implementing a backend, then hit the documentation and you'll find all of the details there. The backends available by default when you install the library are OpenSSL on all of the systems, and on OS X and iOS, Common Crypto as well. And you can use multi-backend to compose backends. So what happens in this case is you construct a multi-backend with a list of backend objects, and that backend then becomes essentially the union of all of the other backends, and when a primitive operation is requested of the multi-backend, it just runs through them until it finds a backend that implements that operation, or possibly doesn't find it and throws an error. So a couple of quick case studies. FreeIPA Vault is a feature in FreeIPA which provides user self-service key escrow or secret storage, which we're looking at integrating with GNOME Password Manager. And also key escrow capabilities. You can store secrets using symmetric or asymmetric encryption. There's a FreeIPA website if you're interested in that feature, but in terms of the implementation, it looks something like this. This is quite simplified. But to encrypt a secret, we basically call encrypt in our library or framework with the data we want to encrypt, and then either a symmetric key or a public key. If we have the symmetric key, we use the FINET construction. Otherwise, if we have a public key, we call the public keys encrypt method, and this is implementing one of the back-end interfaces I mentioned earlier with the data and a padding function to securely pad the data that's being encrypted with the public key. The opposite of encrypt, of course, is decrypt. So to decrypt, pretty similar, except this time we wrap it in a try and catch the exceptions that could be thrown by either the FINET decryption or the private key decryption, which could throw value error, and private key decrypt, again with the same padding function to be used, and the FINET decryption method. So does that make sense to everyone? Pretty straightforward. JW Crypto is a Python implementation of JWS, and JSON Web Signature, JSON Web Token, some of you may be familiar with. This is used by Custodia, which is a secure key distribution service that we're going to be using in FreeIPA. So it implements a whole lot of public key and symmetric encryption algorithms and signing or message authentication codes as well for JWS. So we import from, this time, the Hazmat layer, the asymmetric primitives for padding and RSA, the RSA algorithm. We import the hashes. The pad function we're going to use in this example is PKCS1 version 1.5 and SHA-256. To read the public key, we pull these numbers out of the JWK object, which is a JSON object, and construct an RSA public numbers object. For the private numbers, there's actually a whole lot more parameters for this, but again, we just pull them all out of the JWK. And also there's the RSA pub, which we defined here. So we have to pull the public key out as well to construct the RSA private numbers. For signing, we take the JWK and the payload that we wish to sign. We call private key.signer with a pad function and a hash to acquire an asymmetric signature context object. We update that with the payload, finalize it. So this is basically adding data to the signer to say this is the data we want to be signed across, and finalize that data, and then that returns a signature, and this function returns the signature. And the opposite of sign is to verify. So again, we take the JWK, the payload, and also the signature this time. We extract the public key from the JWK, obtain an asymmetric verification context, and call the verifier with, the context is public key.verifier with the signature pad function and hash function. Similarly to signing, we update that with the payload, and then we call verify, and this will either not return a result, which means it succeeded, or throw an invalid signature exception. So that's just some fairly simple examples of how we're using the cryptography library, hopefully you can see that the recipes layer is extremely easy to use, and the constructions are safe, although they haven't been formally audited. But actually, I'll talk about that now. So there's no memory wiping in this library. So if you have private data in memory, and then those objects are garbage collected, the memory is not zeroed out. So the Python implementation, CPython, doesn't actually provide a way to do that. So cryptography can't do that. In general, if it's dispatching to C libraries that it links to implement some of the backend functions, then they might possibly do that. But the stuff that's implemented in Python can't do that. It hasn't been formally audited, so if you are interested in using it, you need to make sure that it is appropriate for your use cases, that it is secure for your use cases, and you might want to hire a cryptographer to do that. OpenSSL is statically linked on Windows, so every time they find a critical vulnerability and release a new version, if you're using this library on Windows, you're going to have to update. Having OpenSSL updated on the system, unlike on Linux, the next time you load the program, it's going to pull in the updated shared lib. Not so on Windows, so watch out. And use os.urandom for randomness. Conclusion, avoid all low-level crypto where possible, and certainly never ever devise your own cryptographic constructions or try to implement the primitives yourselves. Cryptography has a high-level API for the common use cases and most of the primitives that you're ever likely to need. So in your projects, please consider making it your crypto standard library. And if it doesn't meet your needs, first ask if you are doing the right thing. And if you decide that you are, then that's an opportunity to contribute either by filing a bug report or a feature request, or by implementing bits yourself and submitting a patch. Resources, the docs live at cryptography.io. The code lives under the pyca organization on GitHub. There's the cryptography dev at python.org mailing list, IRC of course. And if you're interested in learning more about cryptography, crypto101.io is an introductory level course that they recommend. That's all. Any questions? Just wait for the mic, please.
Yeah, so this is all basically being done in Python, but for it to be widely used and accepted, you'd have to have it implemented in like all of the common programming languages, right? Otherwise, the systems won't be able to interact with each other.
So this is a Python library for Python programs to consume. But if you're talking about the constructions themselves, like for net, which is relatively new, then obviously if you want to interoperate with another system using the FNET construction, but that other system is not implemented in Python, then they're going to need to, or this other system is going to need to implement FNET or find a library for that language that implements FNET. So most of the constructions, so most of the primitives supported by the library here, where are we? Almost all of these primitives have been around for a very long time, have been well studied, are secure today, as far as we know, although if the NSA is, completely crack SHA-2, then they're not going to tell us about it, are they? So you're going to find implementations of these in just about any language. FNET, the FNET construction is a lot newer, so perhaps not as widely supported at this point. Does that answer your question? Yeah. Yeah, thanks.
So what's the problem you mentioned if a library is statically linked, whether it is on Windows or Linux? What's the problem?
So the problem is, well, the preferred way to approach this is that if a library has a critical bug or a security issue, you can just update that library on your system. Now it's a shared library. That library can be dynamically linked to by other programs. So all that you would need to do is update the library and then, for example, restart your server. It's going to run again and dynamically link the updated version of the library where the security issue is patched. A statically linked library is actually part of the binary that is executed. And if there are critical security issues, it doesn't matter if there's a shared library elsewhere on the system that has been updated. If it's statically linked, it's only going to execute the statically linked code in the executable. So the problem is if there are security issues in cryptography, because it statically links OpenSSL, if OpenSSL has a critical bug, you're going to need to install a new version of the cryptography library on those systems where it statically links OpenSSL.
But it equally applies to a library which is dynamically linked, right? It's just that the loading time is different.
Yeah, so you'll still need to update the dynamically linked library. But on many systems, the default is use shared libs. And so it's just something you have to be aware of if you're using cryptography on Windows. Watch out, it's statically linked. So that's all you need to know. You need to know that it's not enough on that system to simply update the shared library. It's the cryptography library and the shared objects for the cryptography library statically link OpenSSL. So all the OpenSSL code is included in those shared objects.
Just want to ask, if there is a vulnerability discovered and it actually changes the output of the library, so say for some reason one of the padding functions has to change for a security reason, and you're communicating with an older version of the library, will they realize that there's a mismatch, or will it just not work? Hopefully not work.
All of the padding functions, for example, are mathematical constructions. So the idea that the value of the output of a padding function or a digest could change doesn't make a whole lot of sense, because at that point it becomes a different construction. So that situation is not going to occur. If that situation occurs, basically the situation is, the PKCS 1v1.5 padding function is actually fundamentally broken, stop using it. So there's really no provision for, we just need to make this little tweak, but it's going to change the output. It's an all or nothing proposition, basically.
So you mentioned about one of the library, Cryptography, right? It's released under Common Code of Apache license.
Sorry, what was the question?
Is it thread safe?
I believe so.
Okay.
Did you have a... yep.
Really quickly, so can you just go back to, sorry, can you go to the one where you had the warnings, so I think it was the slide before this one.
The conclusion?
Yes, the conclusion. Yep. No, maybe not. Anyway, I guess the point is, when you said it wasn't audited, did you mean the cryptography library is not audited, or the case study that you showed wasn't audited? And if cryptography is audited, do you know what that looks like?
Cryptography library itself has not been audited.
Right.
So there's been no formal security audit, and it just has to come with that warning, because they don't want people to use it and think that it's just an arse covering exercise, which is fair enough.
Who's behind it?
So it was started by Alex Gaynor, and is now in the custodianship of the Python Cryptographic Authority, PyCA.
All right, I'm afraid that's all we have time for. Thank you very much, Fraser.